Welcome back again to our physics class, where for today we are going to be reviewing the topic current electricity. The whole idea about current electricity stems from the generation of current itself. There are so many ways by which you can generate current, but one very common way by which you generate current is through the method of chemical energy conversion to electrical energy. Most of us are familiar with the concept, even in our chemistry, that if we have a vessel and we have a solution of an acid, let us say H2SO4, solution of dilute acid, we call them electrolytes. If we now find two metals that are dissimilar, two dissimilar metals, and we dip them into the solution of the acid, specifically for this purpose, I want to use zinc and copper. If the two of them are connected by a wire, either just together or are connected through a voltmeter, we expect that current will start to flow because there's a chemical process that is going to give birth to that current. Let's just briefly review what the chemical process looks like. We know that if we have a solution of an acid like H2SO4, dilute acid, it will ionize into H plus and SO4 2 minus. Because it is dilute, it will contain large quantity of water, which will also ionize into H plus and OH minus. At the start, the ion move randomly through the solution. But the moment the two metallic electrodes are connected, what we now have is that OH minus and SO4 2 minus will drift to an electrode, while H plus will drift to the other electrode. The positive ion in the solution will drift to one electrode, while the negative ion will drift to the other electrode. If that is done, we have the H plus going to copper to take two electrons, two of H plus will go to copper to take two electrons and become discharged as an hydrogen gas. The hydrogen gas will stay around the copper electrode as bubbles of hydrogen gas for the field that cannot escape. OH minus, so on the copper electrode, what we have taking place is a process that is using electron. Because hydrogen plus goes to the copper electrode, it makes the copper electrode positive. Now, if you have an electrode that is using electron, we should have an electrode that is generating electron. That is the only way there can be a complete flow of electron. If somebody is ready to use, then another person must be ready to give. So when OH minus and SO4 comes to the zinc electrode, we expect either of the two to be discharged, but that will not take place. What will rather now take place is that zinc on its own, now remaining as metal, will prefer to go into the solution. It has an higher potential of going into the solution than for it to discharge any of OH minus and SO4. So what we have is zinc will lose 2 electrons and will go into the solution as zinc 2 plus. I can rewrite this because chemical equations are not written with a negative. I can rewrite this as zinc 2 plus and 2 electrons coming out of that electrode. When that takes place, we say that the zinc electrode is now negative. So this process is such that it continuously generates electrons from zinc, and those electrons are used here in copper. As long as we have zinc, we will have the generation of electron, and as long as we have copper, we will have the usage of electrons. So there is a complete movement and flow of electrons around that circuit. When this takes place, we have charges. The electrons are the charges that are moving around the circuit. that those charges can be measured with the measuring instruments that we'll put here. If you place a bulb here, the bulb will light up because as electron passes through them, we expect that as electron pass through them, we expect that the light will come on. This process, like as I said earlier too, will continue for as long as zinc and copper are there. What we have made is called a simple cell, which can help us to generate current. Though the cell will not work for a long period of time, it will light up the bulb for a short period of time, and almost moments after, it will go off, the bulb will go off. What has happened? It means that there are now processes within it that are disturbing the operation of the cell. Those processes are what we call the defects of a simple cell, and there are just two. One of them is what is called polarization, while the other is called local action. Polarization is the effect whereby the copper electrode or the positive electrode, its surface has been completely blocked or has been majorly blocked by the hydrogen bubbles that it has produced. So once the copper electrode surface is blocked, once the major part of the copper electrode is blocked, it prevents it from having proper contact with more hydrogen ion that it is expected to ionize. So if before it is ionizing like 1,000,000 hydrogen atoms per second, its ability to ionize those hydrogen ion, that quantity of hydrogen ion reduces with time, since the bubbles around it are now insulating it from more ions that is expected to ionize. That reduces the ability of the copper electrode to use all of the electrons that have been generated at the zinc electrode. And once the copper electrode cannot use that amount of electricity, it means that will also affect the amount of electron that zinc is ready to generate. If the copper is not ready to accept too many electrons, zinc will also not be ready to produce too many electrons. That is called polarization. Local action is a defect that occurs due to the fact that zinc, being a very reactive metal, is usually not obtained pure. Because it is not obtained pure, it means that zinc, whenever we use them as electrode, always have other metals that are naturally attached to it. They could be copper, could be iron, could be other metals that have been able to join some part of it from the process of extraction. What will happen when we have impurity on zinc is that there are other materials on zinc that will not behave like zinc. In fact, most of them will start to behave like the positive electrode. What will happen now is you will definitely start to find hydrogen bubbles around the zinc electrode. When hydrogen bubbles are formed around the zinc electrode, it simply indicates that there are components on that zinc electrode that are also behaving like copper. Zinc electrode is not expected to use electron. It is expected to generate electron from the ionization of zinc into the solution. But the moment it starts to use electron and is generating copper, we can say that some of the electron that it is producing are also being used on that electrode. So that generates a condition that we call back EMF, which will impede the safe operation or the smooth operation of this. So our work now as scientists is to ensure that we find a way to reduce the effect of polarization and also reduce the effect of local action. Polarization can simply be reduced by supplying enough oxidizing agent around the positive electrode, such that as those bubbles are being formed, those oxidizing agents will reduce them to water and they go straight into the solution instead of disturbing the proper contact of the electrode with the copper, of the electrolyte with the copper electrode. Those agents that help us to convert most of these hydrogen bubbles to water are called depolarizers. Depolarizers are generally components that are very rich in oxygen. Local action. Local action occur when we use impure zinc. So anytime we have zinc, we must always have the knowledge that zinc is very reactive and most likely there will have been impurities that will be mixed with it in the process of extraction. So what we do is we wash the zinc in with mercury and acid. We wash it in mercury and rinse it in acid. What the mercury will do is to combine with those impurities on it, is to react with those impurities on it and render them inactive, so that when we return the zinc, those impurities will not take part in the process that is going on. That process is called amalgamation, because anytime mercury combines with a metal, it becomes a mercury amalgam of that metal. The essence of reducing polarization and local action is therefore what is necessary for us to ensure that we continue to make this cell work. Now, in practical cells, the idea is to ensure that we find components that we can use to reduce polarization and local action to the BRS minimum. Cell generates current, as we have said. They generate current in terms of electrons that are generated from one electrode and they move to the other electrode. The flow of this electron can also be called charges. The rate of flow of this electron around the cell is what is called the current. So current is simply expressed as the rate of flow of electric charges. The rate of flow of electric charges, and charges can actually be gotten from this equation. Quantity of electric charge can be gotten from this equation as Q is equal to IT. We must have seen this several times also under electrolysis. But anytime we need to find current, is the rate at which charges are moving. When you say you have high current at home, it means you have large quantity of charges moving through a line per time. If you say you have low current, it simply means that you have small amount of electric charges represented by electrons that are moving through a particular point per time. Current, as we know, is measured in coulombs per second. And coulomb is the unit of quantity of electricity. Seconds is the unit of time. So we have coulombs per seconds, and coulombs per seconds easily translates into ampere. Ampere is regarded as one of the fundamental quantities in physics, and it is the unit of electric current. One other thing that the cell ensures is, apart from generating current, the cell ensures that those currents are driven through any component for which such is desired. I just mentioned that if you connect a bulb around a cell, the bulb will light up. Why? Because apart from generating those electrons, the cell also ensures that those electrons are driven through. The electrons are driven through that particular component. Components do not use electron. When your fan is operating, it does not use electron. When your bulb is lighting up, it does not use electron. Components that you have in your house that seems to work on the basis of electricity do not use electron. What happens is electrons simply pass through them. When electrons pass through them, the electron will create an effect in them. There are so many things that an electron can create. Electron can create motor effects. If it passes through a component and the component starts to move, it means it is creating motor or mechanical effect. Electrons can create light effect. If it passes through a bulb, the bulb will light up, and we say it is creating light effect. If it passes through so many other components, if it passes through your television, it creates light. It also produces light effect in your generator, and there are so many other effects that it can produce in all other components. All of these are classified as effects of electric current. Now, what the cell does is, apart from generating the electron, it drives the electron through the component. Such that when the electron passes through those components, it can now create the effect that it wants to create. If it's a loudspeaker, it will create sound effect. If it is a lamp, I've said it will create light effect. If it is a fan, it will create a mechanical effect and it will start to move. The work that the cell will do in moving a coulomb of electricity, I just told you that quantity of electricity is measured in coulombs, and that quantity of electricity depends on the number of electrons that is flowing through. one electron has a charge that can be represented by 1.67 times 10 raised to the power minus 19. So the quantity of electricity equals the number of electrons that we have moving around the circuit. If one electron has this charge, then the quantity of electricity that we are talking about will be the number of electrons. If there are 1 billion electrons, it means 1 billion times this charge in coulombs. So that is what a cell does. Now the cell drives these charges through the circuit. The work that the cell will do in driving 1 coulomb, just a coulomb of electricity around the circuit, is what we call a volt. And a volt is the unit of potential difference. That is one of the quantity that a cell will also introduce to a circuit. If you connect a cell, now represented as this, across a component, most components are called resistors. The cell will drive the charges through this component. It will move through the component and it will continue its motion across. Now the work that is done in driving 1 coulomb of electricity around the cell, around the circuit, is called the volt. The volt is the work done in moving 1 coulomb of electricity across a circuit. So volt is like joules all over coulomb. That is joules per coulomb. And that volt is the unit of potential difference. The cell drives current or charges through a circuit by creating a difference in potential. Of course, what the cell is doing in this case looks like what you would do if you need to move an object from one end to the other end of a table. If you need to move an object from one end to the other and without pushing, what you must do is to create a height difference. As it is, that object cannot go down because they seem to have the same height, so they have the same gravitational potential. The moment you tilt it such that one end goes down and the other end goes up, charges or the object, in this case, will start to move from the point of high potential to this point of low potential. It will roll down all by itself. So what you have created in this case is you have created a difference in potential so that mechanical objects can move from one point to another. So the cell too establishes an electric potential by making the end of one of the components connected to it to be at high potential, electrical this time, and the other end to be at lower potential, so that charges, the electrical body, can easily move from point of high potential to point of low potential. When we draw a cell this way, this point, the longer arm represents the positive point and the shorter arm represents the negative terminal. Cell current can now move from point of high potential, that's the positive end, straight to point of lower potential, that's the negative end. So potential difference and current are two things that we get by connecting an object or a resistor or an electrical component to a cell. When charges pass through a component, we expect now that those charges will be driven through by the cell that the component has been connected to. But the component itself will oppose the flow of those charges through it, because the charges are not just expected to come to the component and leave. There's something they are expected to achieve within the component. If the component is a bulb, those charges are expected to come, create the light effect before leaving. So that creates what we call a clog, which will disturb the smooth flow of the current through it. Now, the opposition that a component will therefore give to the free flow of charges through it is what is called the resistance of that component. Resistance from the English word resist. Components resist the flow of electricity through them. The resistance of conductors are usually measured with in ohms, OHM. Now, materials have different resistance. Materials have different resistance. What we know is that very good conductors have very low resistance. So they do not offer much disturbance, much impedance, much disturbance to the flow of electric current. So current can easily just move through them. But no matter how good they are as a conductor, they will still offer a certain amount of resistance, only that the resistance can be as low as possible, as low as bearable. We have some other conductors that are not that good, whose resistance are a little bit higher, but generally conductors are known to be materials of low resistance, and that is why we generally use them to make electrical components. The higher the resistance, the higher the flow, the higher the opposition to the free flow of current through them. So it becomes a problem when there's too much disturbance to the flow of current. The amount of current that you have in that circuit will have to reduce. If current are finding it difficult to leave, there's no point generating much of those currents. Now, electrical components, I said earlier, have resistance, which is the opposition that they give to the free flow of current. The resistance of electrical components is directly proportional to the length. The longer, for example, if we consider a wire, the longer the wire, the more the resistance of the wire. Why? Because when the wire is very long, if you compare it with a shorter wire, it means it will take some time before the current can transverse through the length of this wire. Whereas if it is short, the current can easily move through it and get to the other end and continue with other parts of the motion that they need to have. So the resistance of a wire is directly proportional to the length. The higher the length, the higher the resistance. That is why if you need to do some house wiring, it is always necessary that you choose the shortest distance possible. Shortest distance means shorter wire, and shorter wire means lower resistance. The resistance of a wire too is also inversely proportional to the area or the cross-sectional area of the wire. The thicker the wire, the lower the resistance. That is why where we need the current to be very high, we use thicker wires. Where you need small amount of current, we use thinner wires. For example, in your phone charger, the wires that you have in your phone charger are actually very small because the current that we have that we need to be supplied to the phone itself is actually very, very small. When you join these two equations together, you see that the resistance is proportional to the length all over the area. If we change this proportionality to equation, we have KL all over A. K is a quantity that can be represented as rho. And if I put that into the equation, I will have R is equal to rho L over A. If you make rho the subject of the formula, you should have RA over L. Rho, therefore, is a constant that we are going to call a name resistivity. Resistivity. Resistivity is a constant about the wire that enables us to determine the resistance if we know the area and the length. Resistance of a material is not constant, but the resistivity of that material is constant. For example, I can cut copper wire that will have a resistance of 2 ohms for you. I can also cut copper wire that will have a resistance of 200 ohms for you. I can cut copper wire that has a resistance of 0.2 ohms for you. What I need to do is to look for the length that will give me the corresponding amount of resistance. But as long as it is copper that I've used to make all these three, it will have the same resistivity. The resistivity of a material is an intrinsic property of a material. It is a property of the material that does not depend on how much of the material you have, Whether you have a small amount of copper or a large amount of copper, the resistivity of copper remains the same. Once you just know the name of the substance, it has a fixed value for its resistivity. And I can now use that resistivity with the cross-sectional area and the length to cut the wire into the exact resistance that I need it to have. Of course, I must also tell you that the resistance of a wire also depends on the temperature of the wire. When you increase the temperature of the wire, the resistance generally increases. That is the concept that we explain that has been used to make a special type of thermometer that we call the resistance thermometer. But for now, we are going to try to see a question that we can solve on resistivity. We had earlier said that the resistivity is Ra all over L. There are times we will need resistivity and they will give us another quantity that is called conductivity. The inverse of conductivity is resistivity. Conductivity is also an intrinsic property of a material. It is a property of the material that is not affected by the quantity of that material that we have. If resistivity of the material is constant, we expect the conductivity to also be constant. Let me take one example on this to see how we can use resistivity. Here we are told that what length of nichrome wire? We're having nichrome wire. We need to know the length of that nichrome wire. What length of nichrome wire? Of diameter 0.20 millimeters. The diameter of that nichrome wire is 0.20 millimeters. If I change that to meters, I should have 0.0002 meters by dividing by 1,000. Now, what length of nichrome wire of diameter 0.20 millimeters and conductivity 9.1 times 10 raised to power 5 ohms? The conductivity is 9.1 times 10 raised to power 5 per ohms per meter. Per ohms per meter. What length of it will give a resistance of 10 ohms? What length of it will give a resistance that is equal to 10 ohms? To do this, all I need to do is to make the length that I need to find the subject of the formula in this equation. If I cross multiply, I will have rho L is equal to Ra. If rho L is equal to Ra, it simply means that the length must be equal to Ra all over rho. If Ra over rho is the length, mind you, I've not been given the rho here, but I can bring it out from this equation. I can say that this should be Ra multiplied by 1 all over rho. I can now say that the length is Ra multiplied by 1 all over rho is the conductivity. So the length must be equal to, the resistance is 10. I need to go and find the area. Remember that most of these wires, in fact, all wires have circular cross-sectional area. So we need to just find it as pi r squared, or where we don't know the radius, we can use pi d squared over 4. Our pi is 3.142 for this question. Our diameter is 0.0002 meters. We divide by 4. We are to square this, mind you. We divide by 4 and we have the answer to the area, 3.142 times 0.0002 squared divided by 4. If we do that, we have 3.142 multiplied by 10 raised to power minus 8. 10 raised to power minus 8. We'll multiply by the conductivity. The conductivity that is given in the question is 9.1 times 10 raised to power 5. If we multiply all of that, we should have 3.142 multiplied by 9.1, and that should be 28.5922 multiplied by 10 raised to power, this is 1, this is minus 8, that's minus 7 plus 5. Minus 7 plus 5 is minus 2. And that is the length. If we take this to ordinary form, we should have 0.286 and that is in meters. So if we have this length of nichrome, based on the values that we are given, that should also be the length that we have the resistance that we need. We'll now move on to Ohm's law. I had established earlier that anytime we have a resistor, if we have a resistor or any electrical component that is connected to a cell, current will move through the cell. I will represent my current as I. The moment we establish a difference in potential across the component, current will move through the resistor the moment we establish a potential difference across the resistor. Now, there is a scientist, the name of that scientist is Ohms, and he's able to give us the law that guides the relationship between the current and the potential difference established across the end. And Ohm's law states that the current passing through a metallic conductor is directly proportional to the potential difference applied across its end, provided temperature and other physical properties are kept constant. I will state that again. The current passing through a metallic conductor is directly proportional to the potential difference applied across its end, provided temperature and other physical properties are kept constant. What the law is indirectly telling us is the current that is passing through the metallic conductor is directly proportional to the potential difference applied across its end, meaning that the higher the potential difference applied across the end of a metallic conductor, the higher the current that is passing through that metallic conductor. So I can also write this as potential difference is directly proportional to the current, because from here, if current is proportional to potential difference will be proportional to the current. So I can make this V is equal to Ki. If I change the proportionality to equation, my K has been found to be equal to the resistance of that conductor. The resistance of that conductor, if I put the resistance R into this equation, I will have V is equal to Ri, or more appropriately expressed as V is equal to IR. And this is the mathematical relationship for Ohm's law. Clearly, Ohms is telling us that the current and the voltage are in direct proportionality, with the resistance of that conductor being the constant between them. That means if we increase the potential difference, we increase the current for as long as we have the resistance of the resistor represented here as R. Potential difference, I told you earlier, is measured in volts, while the current is measured in ampere. The resistance of the conductor is measured in ohms. Please don't forget, it is not all conductors that obey Ohm's law. Conductors that obey Ohm's law are called ohmic conductors. All metals are ohmic conductors. Ohmic conductors are conductors that obey Ohm's law. What we mean by saying that they obey Ohm's law is, for them, the potential difference is directly proportional to I. But for some other types of conductors, yes, potential difference can be established across their end, but the potential difference is not directly proportional to the current that is passing through. It could be proportional to the degree of power 2, or some other type of relationship can exist between the potential difference and the current. Those conductors that do not obey Ohm's law are called non-ohmic conductors. They conduct electricity. Potential difference can be established across their end, and current will definitely flow through them. But they don't do that linearly. The relationship between V and I to them is not linearly. I will call those things non-ohmic conductors. Examples of non-ohmic conductors are electrolytes. Electrolytes are conductors, but they are non-ohmic conductors. Gases are conductors, but they are non-ohmic conductors, because gases do not even conduct electricity at a certain range of pressure and voltage. Now, there are so many other non-ohmic conductors. Diodes, transistors are non-ohmic conductors that we have. But metals, aluminum, copper, constantine, iron, any of it that you can think of, as long as it's a metal, is an ohmic conductor. It obeys Ohm's law. That means for them, we can say that current is directly proportional to the voltage. Now, if we have resistors, how do we arrange resistors? Or before we move on, we have established that the voltage applied across the end of a metallic conductor is equal to the current multiplied by the resistance of the conductor. Now, if we have more than a resistor or conductor that is arranged, number one, how can we arrange more than one conductor inside a circuit? There are two different ways by which we arrange multiple resistors. We can arrange them in series. We can also arrange them in parallel. When you arrange conductors in series, it means that at the end of one, you are putting the other. At the end of one, you are putting the other. At the end of one, you are putting the other. Let's just limit this to 3 resistors, R1, R2, R3. Conductors having resistances R1, R2, R3. For parallel combination, you want to take the 3 resistors and you want to line them together, all joined together at one end and all also joined together at the other end. When you make this type of connection, the resistors are connected in parallel. So when you check in parallel connection, all resistors are connected to the same pair of points. But in series, the resistors are not connected to the same pair of points. If I decide to connect this arrangement to a cell that is going to drive current through them by applying a potential difference across their end, the series connection is complete. If I also connect this one to a cell that is going to drive current through them, by applying a potential difference across them, this parallel connection is also complete. Now, for parallel connection and series connection, we need to check how the voltage or how the potential difference, I can also call it voltage, and the current will fare in each of these type of connection. Now, when resistors are connected in series, it is the same current that will move through them. The current that will move through R1 is the same current that will move through R2, and that's the same current that will move through R3 and back to the cell. Why? Current has to do with the path that is available, and as long as it is only one path that you have created, it is only one current value that will move through all 3 of them. But that is not the same for potential difference. For this cell to drive this current through this potential, each of these resistors, then the potential difference applied across the end of each will be different. Because we know technically that the resistance that each of them will offer to the flow of this current will differ. So if therefore this current is to be driven through different resistance values, then this cell must be ready to apply different potential difference across them. Now, let us assume that the potential difference across R1 is V1. The potential difference applied across R2 is V2, while the potential difference applied across R3 is V3. This is more so important because potential difference is a function of the ends of a component, and if they have different ends, they must have different potential difference. As we've seen here, R1, the ends of R1 are not the same thing with the ends of R2. They are not the same thing with the ends of R3. R1 is connected to the positive part of the cell and R2. R2 is connected to R1 and R3, while R3 is connected to R2 and the negative part of the cell. So we can move on from there. Here in parallel, when the current comes out of the cell, we expect the current to continue with its direction, but until it gets to this point, Now we don't have just a single path, PATH, as we had here. The path at that point seems to be dividing itself into three. There's a path that goes through R1, there's another path that goes through R2, there's a third path that goes through R3. So what will happen is that the current when it gets to this junction, it will divide itself into three. There's an I1 value that will pass through R1, there's an I2 value that will pass through R2, and there's an I3 value that will pass through R3. Of course, after I1 passes through R1, it will come out through this other end. After I2 passes through R2, it will come out through the other end. After I3 passes through R3, it will come out of this end, and the three of them will reconverge and continue their motion at the other end, such that after that junction, they are expected to return back together as I into the cell and also continue another revolution around the circuit. But while the path through R1, R2, and R3 differs, I hope you can see that they all have the same ends. It is the same end that they all have. The same end that they all have all through. They all have the same end all through. So because of that, they will say that they have the same potential difference. What the R1, R2, and R3 connection, what they do not have here is what this one is easily having. They are all connected to the same end. R1 is connected to, if I call this point A, and I call this junction point B, R1 is connected to A and B, R2 is connected to A and B, and R3 is also connected to A and B. So there are simple simplifications that we can make for series circuit connections and parallel circuit connections. I will start from the component that is dividing itself. Here it is the voltage that is dividing. So the cell has a voltage. It has used a part of that voltage for R1, V1, another part for R2, which is V2, another part for R3, which is V3. The component that is dividing itself here is not the voltage. It is only one voltage, and that is the voltage that is being used for the three of them together, since they are all connected to the same ends. But the component that is dividing itself here is the current. The current is dividing itself into I1, I2, and I3. So I can continue. I will say that from here, V must be equal to V1 plus V2 plus V3. Here I can say that I must be equal to I1 plus I2 plus I3. We remember that V is equal to IR. So here I'm going to substitute for each of these voltage values, and here I'm going to substitute for each of these current values. If I do so here, I will say that the V, which is the total V, must be I multiplied by the total R. The nature of the V's must also be the nature of the current. So for V1, there's a current of I1 that is passing through it, and its resistance is R1. I'm just changing the V's to IR. For V2, there's a current of I2 that is passing through it, and the resistance is R2. For V3, there's a current of I3 that is passing through, and the resistance of I3. If we check very well, we have IR is equal to, there's no I1, there's no I2, or there's no I3, or let me say they are all equal. We have already established that earlier, that it is the same current that will travel through all three. So if it is the same current that will travel through all three, I don't need to differentiate them. I can just now factorize, and I will have R1 plus R2 plus R3. If that is the case, I can now say that I should cancel out I, and our R must be equal to R1 plus R2 plus R3. Now I can also substitute for my current. If I substitute for my current, I hope you know from this equation, current can be V all over R. So I'll substitute V over R for each of the current values that I have. This is the total current value that is dividing itself. It will be the total voltage all over the total R is equal to, for I1, I1 is the current value when the voltage is V1 and the resistance is R1. I2 is the current value when the voltage is V2 and the resistance is R2. I3 is the current value when the voltage is V3 and the resistance is R3. But when you check very well, R1, R2, and R3 have the same voltage values. So I'm going to clean 1, 2, and 3 of this. So I will have my V all over R being equal to factorize the V out. If I do that, I will have 1 all over R1 plus 1 all over R2 plus 1 all over R3. If we do that, we'll definitely cancel out the V's. If we cancel out the V's, we have 1 all over R is equal to 1 all over R1 plus 1 all over R2 plus 1 all over R3. And that is an equation that we are going to use to find the total resistance or the equivalent resistance when resistors are connected in parallel. This is the equation that we are going to use to find the total resistance or the equivalent resistance when the resistors are connected in series. So if I have resistors in series and I need to find the equivalent resistance, that is the value of one resistance that will replace all three. If they are in series, this is what I will do. If they are in parallel, this is how I'm going to get the equivalent resistance for the three of them. So we are going to see this in example to see how it can be used. Before we move on, I would also like to talk about the concept of internal resistance and electromotive force. If you take a very old battery or cell and you connect one that is not working, one that has not even worked for years, if you connect a voltmeter across its end, it will definitely read. It will definitely read. Because what you are measuring at that time is what is called the electromotive force. The electromotive force is a function of the terminals of that battery. It's a function of the terminal of that battery. It is like saying that is the power that we believe that this cell should deliver at the point of manufacture. That is what we think this cell, that is what we feel this cell should be able to do at the point of manufacture. If you find the EMF of a new battery, let's say a Tiger battery, you will get 1.5 volts. Check the side of it. That is what is written. If you take one very old Tiger battery and you connect it across a voltmeter, then you find the EMF too, you should get 1.5 volts if you connect it across a voltmeter. The question is, if the new one is reading 1.5, the old one is also reading 1.5, why is now the new one better than the old one? Why will the new one light up your bulb very brightly and the old one will not even do anything, will not even create any effect in the bulb? It is simply because what a cell can do might be seriously different from what it will do. When a cell starts to work for a long period of time, there is an internal resistance that will build up inside it. I had earlier talked about electric cell and the defect of a cell, that cells have what is called experience what is called polarization and local action. Yes, this effect can be minimized, but they can never be completely eliminated. As the cell starts to work, yes, polarization will start to take effect. Yes, you have your depolarizers that will minimize but not eliminate the effect of polarization. So if the cell works for a long period of time, you will naturally expect that the forces of polarization will still catch up with whatever depolarizer you have put there, and ultimately the operation of the cell will be greatly affected. When the cell works for a long period of time, it starts to build internal resistance within it. Resistance are meant to be an external component to the cell, but sometimes even the cell too have resistances. Even the cells create opposition to the flow of the current they are expected to generate within themselves. The opposition to the easy flow of current that is inherent, that is present inside the cell itself, is the internal resistance of the cell. and it builds up with time. It builds up gradually with time, such that if I connect a cell to a resistor, if the EMF of the cell is 1.5 volts, if the cell is very new, it can be using as much as 1.4748 to drive current through the resistor out of this 1.5. But by the time the cell ages, by the time the cell works over a long period of time, out of this 1.5, it can now start to drop the value that is available for the external component. It can drop sometimes even to as low as 0.9 or 0.7 or 0.6. At this point, what the cell is trying to tell you is, yes, I can give you 1.5, but there are certain elements inside me too that are taking away a great part of that 1.5. And once they act, I am only left with 0.9 to do the job that I have been asked to do. So the efficiency of the cell reduces with age. The efficiency of the cell reduces with performance. If I decide now to measure this potential difference across the terminal of a cell, I will get 1.5 and I will call that the EMF. Therefore, I will define the EMF as a potential difference across the terminal of a cell when it is not delivering current. It has not started working. So you think it is good. When it is not delivering current to an external circuit, there's no resistor here that I've connected it to. The only thing I've connected it to is a measuring device. A measuring device do not take any part of the, most of them do not take significant part of the current of the circuit. They don't make the cell feel like it's working. So the cell will tell them what it can do. But by the time the cell starts to work, for example, by the time this cell starts to work, if you connect a voltmeter across it, the voltmeter will read 0.9, and that is exactly what is available for it to drive the external circuit that has been connected to it. This 0.9, I'm now going to call it the terminal potential difference of the cell. The terminal potential difference of the cell is a potential difference across the terminals of the cell when it is now supplying current to an external circuit. EMF is a potential difference across the terminals of the cell when it is not supplying current to an external load, but the terminal potential difference is the potential difference across the terminals of the cell when it is now supplying current. If suddenly I decide to break this circuit so that current does not flow again, the cell that was recording 0.9 as its potential difference will immediately jump back to 1.5. So what reduces the EMF to the terminal potential difference is essentially the internal resistance of the cell itself. The cell has internal resistance values. The internal resistance of a cell will be represented as small letter r, as different from the external resistance that the cell is expected to power. The external resistance is capital letter R. Please don't forget. So when a cell has an EMF, it will use certain part of that EMF to drive current through its own internal resistance. It is whatever is left that you now use to drive current through the external resistance. Like the example that I gave you earlier, if out of 1.5 is using 0.9 for the external resistance, it means 0.6, the remaining part, is being used to solve the problem within itself before it can now supply current to the external resistor that it has been connected to. So I will say that the EMF can therefore be divided into two. It can be divided into the terminal potential difference that is available for the external load, the external resistor, and the lost volts that it is using to overcome the problem that it has within it. Of course, the lost volts is something that is not desirable. We want a cell whose lost volts is as close to zero as possible. So when this takes place, I will say that the terminal potential difference, remember that V is always equal to IR. The lost volt too will be equal to IR, but that R now is for the internal resistance. Whatever the internal resistance takes out of your quantity is a lost value, because it is something that is unaccounted for, it is something that is undesirable. So if I bring these two back into this expression, I will have the EMF is equal to IR plus I small r. The I in this case represents the current that is available in the circuit. The R in this case represents the total external resistor, while the small r represents the total internal resistance of the circuit. Big R represents the total external resistance. E is the EMF. In this question, if they want me to find the terminal potential difference, it is only the current multiplied by the total external resistance. If they want me to find the EMF, I will now think of both the external resistance and the internal resistance. This will now lead us to a percentage efficiency of the cell. Percentage efficiency of the cell can be calculated as what the cell can do, V, all over what it ought to be able to do, multiplied by 100 all over 1. I gave it, the manufacturer gave it an EMF of 1.5. That is what it should be able to do. But upon working, we now find out that the terminal potential difference that is using for our external load is 0.9. So the efficiency will be 0.9 divided by 1.5 times 100 over 1. And I can simplify further by doing my R here is I big R. My E here is I open bracket R plus R. I got that from this expression. If we factorize I out, we will have I plus small r, R plus small r multiplied by 100 over 1. Upon simplification, I can cancel out I, so we have R all over R plus R multiplied by 100 all over 1. Even cells can be connected in series and they can be connected in parallel. Even cells can be connected in series and connected in parallel. We have already looked at resistors in series and resistors in parallel. Cells can also be connected in series and in parallel. How do we solve that? If cells are connected in series, they are connected correctly such that the negative of one leads to the positive of the other. If this is done, the negative of one leads to the positive of the other, the negative of one leads to the positive of the other, and so on and so forth. Let us assume that each of them have an EMF of 2 volts, 2 volts, 2 volts, 2 volts, while their internal resistances is 0.5, 0.5, and so on and so forth. We can combine their EMF. When they are connected in series, the EMF will be the addition of the EMF that we have in the question. That will be 2 plus 2 plus 2 and plus 2. The total EMF in that case will be 8 volts. But their total internal resistance will also be the addition of all of their internal resistances. That is 0.5 plus another 0.5 plus another 0.5 plus another 0.5. So what I'm saying in essence is when cells are connected in series, we add their EMF together and we also add their internal resistances together to get the resultant or the effective EMF and the effective internal resistance. But we have to be very careful when you see cells connected in series. There are instances where those cells, one of them or more than one of them can be connected wrongly. Look at this expression. I said cells are connected correctly in series when negative of one leads to the positive of the other. Negative of one leads to the positive of the other. Here, the negative of one is leading to the negative of one, and the positive is leading to the positive. So you definitely look upon closer observation, or you check, you will discover that this particular cell in the middle seems to have been connected wrongly. If you have that type of cell, it does not mean that the resultant EMF will be equal to 0. No, It will even have, you can connect your Tiger battery, 4 Tiger battery this way. Just make sure that there's one that is connected wrongly. You see that it can still light up your bulb. What we'll do, let us assume that they all still have EMF of 2 volt, 2 volt, 2 volt. What I always ask my students to do is to add those EMF in one direction. Add the EMFs in one single direction. So I'm going to add 2 volts plus 2 volts plus 2 volts plus 2 volts. That should be 8 volts. I will now subtract the EMF of the cell in the opposite direction, like finding the resultant of forces in opposite direction. Those cells that are facing a direction, I will add their EMFs together. The one that is facing the opposite direction, I will subtract its EMF from it. So the answer is 6 volts. For their internal resistance, it will still be the same thing. Their internal resistance will be added together, whether one is facing the other's direction or not. We can also have cells in parallel. Cells can be connected in parallel. When cells are connected in parallel, the resultant EMF let us assume that each of them has EMF of 2 volts, 2 volts, 2 volts, an internal resistance of 0.5, 0.5, and 0.5. If the EMFs are the same, you just pick one, the total EMF will be 2 volts. The only difference here is, here it does not give you a larger EMF. What it does is, it makes sure that only one serves the purpose of powering your circuit. The moment that one dies off or becomes tired, the power continues unabated with the second one and then the third one, and you can even come back to the first one when that has rested a little. So when you have cells in parallel, it can last a very long period of time because one cell will continue to watch out for the other. They will help you to maintain a constant value of the current through your circuit. Now, the internal resistance, the total internal resistance in this case will be obtained from the formula for the total, internal resistance or the equivalent internal resistance for resistors in parallel. So that is how we are going to get their total internal resistance. But there can now be a more technical situation in which the cells do not have the same EMF. Let me use letters this time. Let's say the EMF of the first one is E1, the EMF of the second one is E2, while the EMF of the third is E3. Let me use a more general term to represent the internal resistances too. If the internal resistance of this is R1, that of this is R2, and that of the third one is R3, then I can just easily say that, number one, I will still determine the total or the effective internal resistance from this formula. If that is done, I can now find the total EMF by using the formula E all over R must be equal to E1 all over R1 plus E2 all over R2 plus E3 all over R3. Of course, E1 will be given, E2 will be given, E3 will be given, R1, R2, R3 will be given. We'll go and get R from this formula, knowing R1, R2, R3. With the knowledge of those 7, I can now find the total EMF of the circuit, and that becomes very easy to deal with. At this point, we'll take some questions. We're going to start from somewhere very, very simple so that we progress gradually to more difficult or more challenging parts. We are given a cell of 24 volts. That cell now leads to This is 2 ohms. This is 2 ohms. This is 2 ohms. This is 2 ohms. This is 1 ohm. That is one of the questions we are going to try. Another one is this. We have a current of 10 amperes coming into that junction. We have 12, 6, and 4. 12 ohms, 6 ohms, and 4 ohms. So we are going to start to work with that. We are told here that the current in the 6 ohm resistor shown in the diagram above, the current in the 6 ohm resistor shown in the diagram above is to be determined. What is the current in the 6 ohm resistor? Now I want to find the current in this resistor. To find the current in this resistor, I need you to understand that we said for a parallel connection, when current comes to a junction, it will split itself into 3. If it splits itself into 3, we'll have I1, I2, I3, because there are 3 branches in that junction. What I will first do in attempting questions either in series or parallel, as we have here, is for me to try to attempt to find the total condition. I'll find the total I. Luckily, that has been given as 10 ohms. The undivided current is the total current. But by the time it comes into this branch, it divides itself into 3. I'll find the total R and I'll find the total V. If I want to find the total R, because they are obviously in parallel, I will use 1 over R is equal to 1 over 12 plus 1 all over 6 plus 1 all over 4. If that is the case, I have 1 all over R is equal to, I'll find the LCM of 12, 6, and 4. That is 12. 12 divided by 12 is 1 times 1 is 1. 12 divided by 6 times 1 is 2. 12 divided by 4 times 1 is 3. So I should have 1 all over R is equal to 6 all over 12. I should have R being 12 all over 6. If R is 12 all over 6, it will be 2 ohms. So the total resistance for this circuit is 2 ohms. I can now find the total voltage. If I need to find the total voltage, I will use my V is equal to IR. Once I use my V is equal to IR, I will have V is equal to 10, that's the total I, multiplied by 2, that's the total R, or the equivalent R. That's 20 volts. Now, since I know the total V, let me now show you the total V. The total V in this parallel connection is the V across the point that they are all connected to, 20 volts. That's the total V. So V is equal to IR is always very, very important. You can use it for the total condition. You can also use it for specific conditions. When we say specific condition, now that I've used it for the total, I can now use it for each of the resistors. And since the resistors that I've been asked to solve for is 6 ohm, I will just use my V is equal to IR for this 6 alone. The V of that 6 is 20. In fact, that should be the V. That is the V for each one of them. If I ask you for the V of 12, is 20. The V of 6 is 20. The V of 4 is 20. Why? I told you earlier that when resistors are in parallel, they will have the same voltage applied across their end. So I know the voltage of 6 to be 20. I can also use it for 12. I can also use it for 4. So that's 20 is equal to the current across 6 is I2. That's what they want me to find. What's the resistance of that line? 6. It is 6. I2 therefore must be equal to 20 all over 6. 20 all over 6 should be 10 all over 3, and 10 all over 3 should clearly be 3.33 amperes. That is the answer to the question. We'll take more questions before we now come back to the one I have on my left hand side. In the circuit diagram shown above, what's the potential difference across the 25 ohms resistor? Across the 25 ohms resistor, there's one more information in the question. We are given the potential difference for this to be 14 volts. We want to find the potential difference across the 25 ohms resistor. Whatever they want you to find, please indicate it. Like I said earlier, the very first thing to do is to get the total condition. Get your total V, your total I, and your total R. The total V is given. That must be the V of the cell. The total I is not given, but I can find it. The total R is not given, I can also find it. When resistors are in series, this is a series connection of resistor. When resistors are in series, I can add them together to get their total resistance. That will be 25 plus 50 plus 100. 25 plus 50 plus 100. And the R must be equal to 25 plus 50 plus 100 is 175 ohms. My V is equal to IR for total condition. I must be equal to V all over R. The total V14 divided by the total R175 should give me 0.08. 0.08 amperes. If that is the case, I can now find the voltage across. So what I'm saying in essence is the current passing through the circuit is 0.08. It will pass through the circuit. That's the current that will pass through 25. It's the same current that will pass through 50, and it's the same current that will pass through 100 and come back to the cell. If that is the case, I can now find the voltage that is required. That's the voltage across 25. The voltage across 25 will be equal to I will just use V is equal to R. I told you that V is equal to R can be used for the general circuit. It can be used specifically again for one resistor. I want to use it for 25. Since the question is set for 25, my current is 0.08 and my resistance is 25. If I decide to multiply the two, I should have 0.08 times 25. That is 2 volts. It means the voltage across the 25 ohms resistor is 2 volts. I can now move on to the one that we really need to solve. That we'll try to see if we can even take more questions. Now we have a circuit. The circuit looks a little bit difficult to even understand, but it is easy. In fact, it is not harder. It is not in any way harder than those ones that we have seen. The shape can look confusing, but you can always try to unravel it by tracing the path of the current through the circuit. Understand that all current must come from the cell. So when the current goes through the circuit, when it gets to this point, know that it is going to divide into two. So the question is, how many branches is it going to do? How many parts is it going to divide into? It has 2 branches. There's a part that is passing through these 2. There's another part that is passing through these 2. So this current will divide itself into 2. One will pass through 2 and continue with 2, then get to another junction. Let's assume it will wait there. The other one will pass through 2 and also pass through another 2, get to this same junction, and the 2 of them will just continue their paths. So if you want me to simply redraw this in the form that we have been working, I will say that, okay, current, the cell releases current. The current will divide itself into two parts. One part will pass through 2 ohms. The other part will also pass through 2 ohms. 2 ohms and 2 ohms. That is what we have here. On the other branch, we have another 2 ohms, another 2 ohms. So, and that is the end of that part. By the time the two of them converge, it is the total current that will now pass through this one. So you can see that the total current is passing through this one. So this one is not part of the parallel connection. It's standing alone. So I can draw it like this. The one is standing alone. And I can now just connect everything back to my cell. This circuit and this circuit are just the same thing, 24 ohms. And we can easily interpret this one. Let us see the question. What do they want us to find in the circuit? We are asked to determine the current through the 1 ohm resistor. What is the current through the 1 ohm resistor? The first thing I need you to do is to find the total condition. Let us get the total condition. Now, this is meant to be a parallel connection. The only difference now is on this line, on this branch, we have a 2 ohm and another 2 ohm joined together in series. We have another 2 ohm and 2 ohm joined together in series. So we have two parallel connection of 2 ohms on each branch. So we are going to, what I want you to do is just add these two together because they are in series. Since they are on the same line, if they are in series and on the same line, it becomes 4 ohms. I can add them because that is how we treat resistors in series. I'll do the same thing here. 2 ohms and 2 ohms that are in series should give us 4 ohms. So now the circuit is becoming easy to handle. We have 4 ohms and 4 ohms in parallel. So if I want to find the total resistance, it will be 1 over R is equal to 1 all over 4 plus 1 all over 4. It will be 1 all over R is equal to 4, 1 plus 1. To be 1 all over R is equal to 2 all over 4. If we turn this, R will be equal to 4 divided by 2. R becomes equals to 2. So the total resistance of the whole of this parallel connection is 2 ohms. I can even clean it and just replace it with that 2. And that is when I will observe that it is just 2 resistors that we have in the circuit. So the total resistance now, since I know that this 2 is in series with 1, the total resistance will just be 2 plus 1, and that should be 3 ohms. My voltage is given to be 24 ohms. Because it is 24 ohms, I can now find the current. The current is V all over R. My V is 24, and my voltage, my resistance is 8. The current should be 8 amperes. And because the one is standing alone, we expect that the current that will pass through it is the total current, and that is what I've been able to find. We'll take more examples. This time we are going to take a word problem. The question says that a battery of EMF 4 volts and internal resistance 1.0 ohms is connected to a 9 ohm resistor. We are asked to draw a circuit diagram and calculate the current that flows in the circuit. The second part, a cell of EMF 1.5 volt and internal resistance 2 ohms is connected to two 6 ohm resistors in parallel. Calculate the combined resistance of the two 6 ohm resistors in parallel, the current supplied by the cell, and the terminal potential difference of the cell. If I need to solve one, I will pick the second. A cell of EMF 1.5 volts. We have a cell of EMF 1.5 volts. We are told that it has internal resistance of 2 ohms. It also has internal resistance of 2 ohms. It is now connected to two 6 ohm resistors in parallel. It is connected to two 6 ohm resistors in parallel. This is connected to two 6 ohm resistors that are placed in parallel to each other. Six ohms, 6 ohms. If that is the case, we are told that we should calculate the combined resistance of the two 6 ohm resistors in parallel. The combined resistance of the two 6 ohm resistors in parallel. The combined resistance will be 1 all over R will be 1 all over 6 plus 1 all over 6. So the combined resistance will be 1 over R, which will give us LCM is 6. 6 divided by 6 times 1 is 1. 6 divided by 6 times 1 is 1. 1 over R, therefore, should be equal to 2 all over 6, and R must be equal to 3. The total resistance of this circuit, the total resistance of the two 6 ohm is 3. We have to find the current supplied in the cell. The value that we are given now is EMF, so we use the formula for our EMF. Because there's now an internal resistance, EMF should be equal to I open bracket R plus R. We gave that earlier. So our EMF 1.5 must be equal to our I. We don't know the value, but we know our total external resistance is 3, and the total internal resistance is 2. That means 1.5 is equal to I multiplied by 5, and my I will definitely be 1.5 divided by 5. That should be 0.3 amperes. If that is the case, we have to find the terminal potential difference of the circuit. The terminal potential difference, if you break this bracket, you have E is equal to I open bracket R plus R. The terminal potential difference is the part that you get when you multiply the current by the total external resistance. That is the terminal potential difference. So our V is equal to the current 0.3, and our total external resistance is 3. The answer is 0.9 volts, and we can clearly see that while the EMF of this cell is 1.5, the terminal potential difference that is available for our external component is 0.9 volts. We can be asked to find the percentage efficiency of the cell. If we need to find the percentage efficiency of the cell, it will be the terminal PD divided by the EMF multiplied by 100 over 1. The terminal PD is 0.9, the EMF is 1.5. If we multiply this by 100 over 1, we should have 3 all over 5, because 0.3 here is 3, 0.3 here is 5, times 100 over 1. If we solve that, we should have 60%, which is the percentage efficiency of the cell that has been given. We'll move on to measuring instruments. There are 3 basic measuring instruments that we should talk about, though we are still going to extend them to more. Number 1, we have the voltmeter. The voltmeter is represented with a circle that has a V. The voltmeter is used to measure the EMF. It can be used to measure the terminal potential EMF and the terminal potential difference, the EMF, and the terminal PD. We have the ammeter. The ammeter is used to measure the current. It's used to measure the current. Now, how do we use them in a circuit? If we have a resistor that is connected to a cell, the current, let us assume that the current is of the value of I. If I need to measure that current, I must put the ammeter along the line that the current is going to pass through. I must put the ammeter along the line that the current is going to pass through. Now, if I am going to put ammeter like this, it means I have placed the ammeter in series. Generally, when you put components in series, their resistance will add to the resistance of the circuit. For example, we know that if we have two resistors in a circuit, their resistance will add to each other. Their resistance will now become 5. So if we are to connect ammeters in series, and the function of that ammeter is not to significantly affect the values that we are going to have in our circuit, and it is yet to be connected in series, it means ammeters must be made with materials of very low resistance. It must be made with materials of very low resistance so that its resistance will not significantly add to the resistance of the circuit, a situation that can reduce the current we are expecting out of this system. So ammeters are generally made with materials of low resistance because they are connected in series, and we do not want them to add significantly to the resistance of the circuit, a situation that can further reduce the current that we can get. Voltmeters are usually connected in parallel. The problem of voltmeters or components that are connected in parallel is that when current comes and gets to a point, those voltmeters seems to create an alternative path to current. If current gets to this point, current will now want to divide itself into two, such that a part of it will pass through the voltmeter and a part of it will pass through the resistor. If that is the case, it means this voltmeter will not measure what is expected to measure. For example, measuring instrument must not partake in the process of sharing current. If the current that is coming in is 2 ohms and the resistance of this resistor is 3, I expect this voltmeter to record something very close to 6, because V is equal to IR, and the I that is coming into the line, since this is the only resistor, is 2. The resistance itself is 3. If we multiply them, we should have 6 amperes, 6 volts. So we expect this voltmeter to record a value of 6 volts. But if it has been made with a material whose resistance is very low, we know for sure that current, when they get to a junction, more current will go through the path with the least resistance. If the voltmeter is made with a material whose resistance is less than 3, or even of the order of 3, it will share these two with the resistor. If it shares these two with the resistor, it could be that the only part of these two that will move through this resistor is 1. And in that case, the voltmeter will now record 1 instead of the 6 is expected to measure. So we do not want voltmeter to take any part of the current that is expected to pass through a resistor. That way, we will achieve it by ensuring that the voltmeter is made with materials of very high resistance. The higher the resistance, the less the amount of current that will pass through it. If its resistance is so high, of the order of, let's say, 300 ohms, much of these 2 amperes will pass through the 3. And if there's any part of it that will pass through the voltmeter, it will be so negligible, such that the voltmeter will still be able to record what we want it to record. So voltmeters are connected in parallel. They are made of high resistance so as not to divert a significant part of the current that should pass through the components through themselves in a circuit. There are now what we call galvanometers. Galvanometers are used to measure very small amount of current. Galvanometers have other name. They can be called milliammeter because they do what ammeters also do, but they measure small amount of current. We represent galvanometer with a circle that has a G, but can also be represented with a circle that has an arrow pointing in any direction. So I told you that galvanometers can also be called milliammeters. If ammeters have very low resistance, galvanometers will have even lower resistance. It means that if I am to use galvanometers in a circuit, I expect their resistance to be very low so that they do not partake in the process of taking any part of the current. There are now aspects that we should move to. We can convert galvanometers to ammeters, and we can also convert galvanometers to voltmeters. How do we achieve this? Ammeters are used to measure current. Galvanometers are used to measure small amount of current. It means that if I have a line that has a galvanometer, I'm expecting the current along that line to be very small. Let us now assume that the current that is coming through this line is more than what the galvanometer can measure. We are always given the full scale deflection of a galvanometer. The full scale deflection of a galvanometer is the maximum current that galvanometer can measure. Let us assume that the full scale deflection of this galvanometer is 0.1 ampere. That means that's the maximum current that this galvanometer can measure. We now have a line where 10 ampere is passing through, is expected to pass through. Of course, if this 10 ampere is exposed to this galvanometer, it will damage it because it is now going to be exposed to a current that is more than what it has been designed. So what we will do in this case is we'll connect a low resistance material in parallel to it. We'll connect a low resistance material in parallel to it. We'll connect a low resistance material in parallel to it. We'll expect that it should be a material whose resistance will be so low that when this 10 amperes gets to this junction, much of it, the excess current will be diverted through it, and only the maximum current that this galvanometer can measure will be allowed to pass through. So if 0.1 is allowed to pass through, it means this must be such that it will allow the remaining 9.9, that's 10 minus 0.1, to pass through it. And that galvanometer will be safe from the damage that this 10 amperes can cause to it. If this is to be the case, we'll call this material of very low resistance a shunt. Shunt is a resistor of very low resistance, and I can now be asked to find the resistance of the shunt. If I am asked to explain how to convert galvanometer to an ammeter, I'll say that I'll connect a shunt in parallel to it. So if I want to find the resistance of the shunt, what I will do is I will say that since the shunt and the galvanometer are in parallel, the voltage across the shunt must be equal to the voltage across the galvanometer. That means clearly that if I use my V is equal to IR, why are the voltages even the same? Because when components are in parallel, the potential difference across their end, the two of them are connected to the same end, so the potential difference across their end must be equal. It means that for this, the voltage across the shunt will be I across the shunt, R of the shunt, must be equal to I across the galvanometer, R of the galvanometer. The R of the shunt will therefore be determined as I of the galvanometer, R of the galvanometer divided by the I of the shunt. If I know the I passing through the galvanometer, in this case 0.1, I'll be given the resistance of the galvanometer. I'll divide it by the current passing through the shunt, in this case 9.9, and it will give me the resistance of the shunt that will do this job for me. How do I convert the galvanometer to a voltmeter? How can I convert the galvanometer to a voltmeter? Galvanometers generally, because of their very low resistance of the galvanometer are actually very low, and the current that is expected to pass through them is also very low. The current that is expected to pass through the galvanometer is very low. So if we find the potential difference across the galvanometer, it is usually also very low. The potential difference across the galvanometer must be equal to V is equal to IR. That's I of the galvanometer multiplied by R of the galvanometer. If we multiply two very low values, we'll get an even low values. We can now be told that how can we increase the voltage across the galvanometer to be very high in value. What we will do in this case is we will connect an high resistance resistor in series with it. An high resistance resistor in series with it. Example of such high resistance resistor is called a multiplier. Any resistor that has high resistance is called a multiplier. The resistance of the multiplier will be so high that when added to the resistance of the galvanometer, it will increase that resistance and therefore increase the voltage that we can get across this system, and we can easily solve for it. We'll take example on this and we'll continue. A galvanometer has a resistance of 2 ohms. We have a galvanometer whose resistance is 2 ohms and a full-scale deflection of 15 milliamps. It can only measure a current of 15 milliamps. 15 milliamps, if I have to change that to amperes, it is 15 divided by 1000 to be 0.015 amperes. So the current through the galvanometer must be 0.015 amperes. Now, if that is the case, the shunt that will do this job for me must be a shunt that will divert the excess current through itself, and that will be 1.5. The current through the shunt must be 1.5 minus 0.015, and that should be 1.485 amperes. So I want a shunt that will be able to divert 1.485 amperes through itself. I can say that the voltage across the shunt must be equal to the voltage across the galvanometer. If we break this down, I shunt, R shunt must be equal to I galvanometer, R galvanometer. I want to find the R of the shunt, and that will be I of the galvanometer, R of the galvanometer divided by I of the shunt. The I of the galvanometer must be 0.015. The resistance of the galvanometer is given to be 2, while the current passing through the shunt must be 1.485. If we do that, we'll get 0.015 times 2 divided by 1.485. The answer is 0.02. So the shunt that I need must have a resistance of 0.02. If I want to explain it, I'll say that I'll connect a shunt of 0.02 in parallel to the galvanometer. That is just one side of the question. The other side of the question is asking us that how do we convert this same galvanometer whose full-scale deflection is 0.015 amperes and whose resistance is 2 ohms. How do we convert it to a voltmeter which can measure voltages up to 30 volts? Let us find, as it is, let us find the voltage of the galvanometer. The voltage of the galvanometer will be I of the galvanometer multiplied by R of the galvanometer. As it is, the voltage is 0.015 multiplied by 2. That should be 0.03 volts. We now want to convert it. So the potential difference across it is just 0.03 volts. We want to convert it to a voltmeter whose voltage will be up to 30 volts. Of course, that can only be achieved if we try to increase one of the 2 components of the galvanometer. We cannot increase the current through the galvanometer to damage it, but we can increase the resistance by connecting one high resistance resistor that I call the multiplier in series with it. If that is done, then I can now use my V is equal to IR for this whole component. My V that I want to achieve is 30. The current that is passing through that line is 0.015. The resistance will now be the resistance of the galvanometer plus the resistance of the multiplier. That will be 30 divided by 0.015. It must be equal to resistance of the galvanometer is 2 plus resistance of the multiplier. 30 divided by 0.015, 30 divided by 0.015 should give us 2000. 2000 is equal to 2 plus the resistance of the multiplier. So the resistance of the multiplier must be 2000 minus 2. And 2000 minus 2 is 1998 ohms. That's the resistance of the multiplier that must be connected in series to the galvanometer to convert it to a voltmeter that is capable of measuring up to 30 volts. So that is the end of that. We will now move on to other measuring instruments. We'll just touch on them one after the other. We have measuring instruments that can be used to measure the resistance of a resistor. There are two of it. We have one that is called the Wheatstone bridge. The Wheatstone bridge is such a circuit that is made up into this form. The Wheatstone bridge measures the resistance of a resistor by using three other standard resistors. The arrangement is what is shown above. I'll create a circuit where there will be an arrangement of four different resistors. Let's say this is resistance A, and this is resistance B, this is resistance C, and this is resistor that I want to find this resistance. Now, I want to find the resistance of this resistor, but I must have three other standard resistors. I will now I'll connect a galvanometer across the three, and I will supply current to this circuit. I will now start to alter A, B, and C using different values of resistance. At what point will I stop? The moment this galvanometer gives a zero reading. The moment the galvanometer gives a zero reading, I'll say there is a balance point. And once there's a balance point, I can now write an equation of the ratio of the resistance on each side. Once this galvanometer gives a zero reading, I can clearly say that my RA all over my RB must be equal to Rx all over RC. The ratio of the resistance on this side must be equal to the ratio of the resistance on this side. And that will give me the value of Rx. If I know RA, RB, and RC, that will make this galvanometer to record 0. I can also take the ratio. I think I can also take the ratio as RA all over. I can take any adjacent pair of resistance. I can say RA over Rx is equal to RB all over Rx. I can take RA over RB is equal to Rx over RC. I cannot just take opposite pairs. That's what I must not do. I can only take adjacent pair, and that is just what is there for the Wheatstone bridge. We have the meter bridge. The meter bridge is also designed to measure the resistance of an unknown resistor. What you need to do is to get a wire on a meter rule. That's why it's called a meter bridge. A wire on a meter rule. One end of it is connected to a cell. You can have a switch. You can have another standard resistor to ensure that the current does not become too high. And on the other end, you will now connect two resistors. One of them must be the resistor that you want to find its resistance. Let us say this is the resistor. I'll call it Rx. The other must be the resistor that you know the resistance. Then that must be a standard resistor. So I will determine the resistance of an unknown resistor when I'm giving the resistance of a standard, when I'm giving the resistance or a standard resistor, one that I know the resistance of. And just between the two, I'll connect them to a galvanometer. I will connect the galvanometer to my jockey. I will now start to touch different points on my jockey until this galvanometer records a value of 0. The point where this jockey is, where this galvanometer records 0, upon the connection of the Rx, the resistor I want to find the resistance, and RA, the resistor that I already know the resistance of, is the balance point or the balance length. I'll measure the length from here to that point, from one end or the 0 end to that point. I measure the length from here to that point. Let me call this length L. If it is a meter rule, it means this other end will be 100 centimeters or 1 meters minus L, because 100 centimeters is equal to 1 meter. I can now say that the ratio of the resistances must be equal to the ratio of their corresponding lengths. So I can say that Rx all over RA must be equal to L all over 100 minus L. And that way, I'll be able to know Rx if I know the length. From there, we move on to the measurement. Another device that can be used to measure the EMF of a cell. It looks very much like a meter bridge, but it is called a potentiometer. It can be called a potentiometer. A potentiometer is instead used for accurate measurement of the EMF. We will set up a potentiometer circuit like what I showed you earlier. There will be a cell, there will be a key, and there will be a resistor. Then I will have the whole arrangement connected to a wire that is on a meter rule. I will take a cell that I already know the EMF, I'll connect it to a galvanometer, and I'll get the balance length. The balance length is the length that I will put the jockey on this wire, where the galvanometer will record 0 for this cell. If that is the case, let me say that the EMF of this cell is E1, and I'm getting a balance length of L1. I'll keep those values. I will now remove this cell and I'll put the one that I want to find the EMF of. Let me say that the EMF of that is EX. I don't know the value of EX. I will now get the balance length for this other cell. Let us assume that the balance length is now at this point. Let me say that the length for that is LX. What I am saying in essence is that there is a direct relationship between the EMF of the cell and the length of the length that will balance that EMF. In that way, I can say that E is equal to KL. So E all over L must be a constant. So I can now say that my E1 all over L1, the cell that I used before and the L that I got before, must be equal to EX all over LX. And that is the equation that will give me the EMF of the cell that I want to determine, and if I know the other 3 values that I used in that equation. There are other instances where I will not even be given a balance, I will not be given a standard cell at all. If I'm not given a standard cell, I will need to know the potential difference across the whole of the length of the wire. The potential difference across the whole of the length of the wire is what I will use. This time the length is 0, is 100, because it is the whole of the length of the wire, is what I will use to determine the EX all over LX. We are going to solve question on this, and we are going to try to use that question to exemplify what we're talking about. So let's take one question apiece for Wheatstone bridge, meter bridge, and potentiometer. Then we'll end this topic. We have I have a 45 ohms resistor. I have a 15 ohms resistor. I have a 30 ohms resistor and R, 30 ohms resistor and R. This is, now the question goes thus. In the diagram above, the galvanometer G indicates a null deflection. That means a zero deflection. Use the information to determine the value of R. Use the information to determine the value of R. The value of R will just find the ratio. If we do the ratio of this, it will be 45 all over 15 must be equal to 30 all over R. And if that is the case, we'll cross multiply. We have 45 R is equal to 30 times 15. We'll now say that R must be equal to 30 times 15 divided by 45. 15 here 1, 15 here 3. R should give us a value of 10 ohms. And that is the final answer. There's another question that we should look at on meter bridge. We have 4 ohms. This is 4 ohms. We are told that this is X and this is also X. We are not given the value. We have a galvanometer, we have a meter bridge in the middle. It's a galvanometer that recorded a balance point of 40 centimeters from this end to the other end. We are now asked, the cell is given, we are told that in the diagram above, a balance point is obtained at 40 centimeters from the left end. Find the value of X. The balance point is obtained at 40 centimeters from the left end. Find the value of X. This other side should be 60 centimeters because, except otherwise stated, we always take this to be 1 meters. So the resistance that we have on this side, all over the resistance that we have on this side, must be equal to the ratio of the length. The length that you have here, the length that corresponds to this, all over the length that corresponds to this. But when you look at this, it looks like a parallel connection of X and X. So I will try to combine them. I will say that 1 all over R, since they are in parallel, is equal to 1 over X plus 1 over X. It means that 1 all over R, the equivalent resistance for X and X is X divided by X times 1, 1. X divided by X times 1, 1. So 1 over R is equal to 2 all over X. It means R itself will be equal to X all over 2. If R is equal to X all over 2, then I can now do the ratio of the resistances must be equal to the ratio of the length. That means 45 divided by X all over 2 must be equal to 40 all over 60. If we do that, we have 45 times 2 all over X is equal to 40 all over 60. 0 cancel out 0. We have 90 all over X is equal to 4 all over 6. If we cross multiply, 4x is equal to 90 times 6. We divide both sides by 4. We have X is therefore going to be equal to 2 here 2, 2 here 3, 2 here 1, 2 here 45. 45 times 3 is 135 ohms. Then the last question, to test our knowledge on potentiometer. We are told that a potentiometer circuit consists of a 1 meter long wire. It's a 1 meter long wire of resistance 5 ohms. The resistance of this wire is 5 ohms. The resistance of the wire is 5 ohms. Connected in series with a 4-volt accumulator, an internal resistance of 1. It's connected in series with a 4-volt accumulator. Accumulator is a cell, 4 volts, and it's having internal resistance of 1 ohms. That's about all. The potentiometer circuit is what they have given to us. The first question is, we should find the total resistance of the circuit. The total resistance of this circuit must be equal to the internal resistance 1 plus the resistance of the wire 5. And the total resistance is equal to 6 ohms. What's the current flowing in the circuit? What is the current that is flowing in the circuit? We use the formula E is equal to I open bracket R plus R. These are just simple resistor questions. The E is given to be 4. I we don't know, but we know the total R. We have just calculated it here, 6. So I must be equal to 4 divided by 6. And that should be 2 all over 3, which is 0.67 amperes. What's the potential difference across the potentiometer wire? What is the potential difference across the potentiometer wire? If I want to find the potential difference across the potentiometer wire, I will just use V is equal to IR. I will treat the wire like a resistor. The current in that case will be 0.67. The resistance will be 5. If I multiply 0.67 by 5, the answer is 3.35 volts. 3.35 volts. Now we have a follow-up question. The potentiometer circuit above is now used to measure the EMF of a dry cell. The balance length of 80 centimeters is obtained. What is the EMF of the balance length? What is the EMF of the cell? Mind you, when they found the potential difference across the whole of the wire, across the 100 length of the wire, it is 3.35. We now use it to measure the EMF of a cell. We don't know the EMF of that cell. And we recorded a balance length with a galvanometer. We recorded a balance length of 80 centimeters. What is the EMF of that cell? So we simply do V all over 100. The V is the total potential difference of that 100. And that is 3.35. The total potential difference over 100 is equal to EX all over 80. If we need to do this, EX must be equal to 3.35 multiplied by 80 divided by 100. The answer should be equal to 3.35 times 0.8. And our answer will be 2.68 volts. That is all about that. And with that solution, we have come to the end of this very interesting topic. I hope we have all enjoyed it. Thank you very much for your attention.